Hi, in this video, I want to look at an example where we are passing a noise, which is the noise which was in the exercise that I had put. So you have a uniform white noise with an amplitude of 20 nanovolt per root hertz. Okay, so that's the power spectral density amplitude, and the amplitude stays constant for all frequencies, and this noise is inputted to a system, and this system is basically a first order low pass filter with an R of 1 kilo ohm and a capacitance of 0.159 microfarad. And what we want to see is what do we get at the output, or more specifically what we want to find out is the RMS voltage of the noise at the output. Okay, V out RMS. So the basic idea here is that this noise is going to be filtered by this first order filter, right? So we just looked in the previous video that if you have a noise of a particular amplitude or a shape, and you have a filter whose gain is AF, then basically the noise amplitude and the gain of your filter get multiplied, right? And then we can find out the RMS value. So let's do that. So first of all, let's try to find out what our gain for this filter is. Now, without any proof, I'll just write here that the transfer function of this filter is going to be 1 over 1 plus S over 2 pi f naught, where f naught is the cutoff frequency of this filter and is given by f naught equal to 1 over 2 pi RC. And you can calculate this cutoff frequency and you will find that it's going to be 1 kilohertz. Okay, so if you wanted to plot AF, and you can do that as an exercise. We've done that in medical instrumentation 1, so I'm going to leave that as an exercise to you. If you have frequency here and I say, well, I want to plot the frequency response of my filter, this is how it will look, right? This is approximate, but somehow something like this, and your cutoff frequency here is going to be 1 kilohertz. Okay, so now what we want to do is we want to multiply this frequency here with this frequency response here, and of course you can convert it into AF, right? So if you replace S with what is S going to be? S is basically 2 pi f, right? So S is going to be J omega, and that is going to be equal to J times 2 pi f. So if I substitute this into the equation here, what do I get? So let me write that. So 1 over 1 plus J f over f naught. So that's what I get. And perhaps what we want to do here is find out the magnitude of this. So if I find out the magnitude of AF, I get 1 over 1 plus f over f naught square. And you'll have a square root around this, right? So that's going to be the magnitude. And what we want to do, of course, I should have mentioned this before. What I'm plotting here is the magnitude here. Okay, so now what I want to do in this exercise is I want to multiply V in with the magnitude of the amplitude response. So I want to multiply V in F times AF, right? And that gives me the spectral density, the root spectral density of the output noise. I square it and I integrate it. Where do I integrate it from? I will integrate it from 0 to infinity. And if I do that, I should get V out RMS square, right? So let's evaluate this in the next slide. Okay, so let's do this integration and see what we get. Okay, so if you, so what is V in of f? It's basically 20 nanovolts per root hertz, right? So you can write it 20, and that's all there is, right? And then mod AF is basically given by the equation here. So I substitute it into the equation, and so I'll get in the denominator, I'll get 1 plus f over f naught square. I've just squared it already, so I'll write 20 square here, and let me remove this dot here. Okay, so that's what I get, and I'm going to integrate this from 0 to infinity. So if I integrate this from 0 to infinity, what do I get? Again, let me just write this without any proof. I'm sure you will be able to do the integration. What you get is tan inverse f by f naught. And what I want to do is I want to evaluate this f by f naught from 0 to uh, infinity. You can evaluate this, and what you're going to get is approximately 6.28 times 10 to the power 5, and this is going to be in nanovolts square. One of the ways to think about this is that tan inverse, if you put infinity here in this equation, tan inverse infinity is going to be pi by 2, and tan inverse 0 is going to be 0. So you get 20 square times f naught, which is 1 kilohertz, as we calculated previously, and you would be subtracting pi by 2 minus 0, right, for the infinity and 0. And so you get this, and from here you can write your V out RMS equal to, and it's basically a square root of this value, and what you get is you get 0.79 microvolts as the RMS value. Hope that is all right.